We're not out of danger yet. The Savara is locked into a decaying orbit.
August, get our systems back up and running, do whatever it is. Just give me something to get us away from that fucking star.
They claim the James Webb Space Telescope spotted a large object about 10 light years away moving toward Earth. The Post's claim that the telescope captured the object changing its trajectory.
This isn't science fiction. It's happening right now. Quantum computing decoding messages from the stars and what it found in 3 I/ATLAS.
This object, already remarkable for being only the second interstellar comet ever identified, has shown signs that suggest the presence of something alive, or at the very least biological in nature,
is unlike anything we've ever seen. The results from analyzing 3 I/ATLAS using quantum computing and machine learning algorithms are revealing patterns that human scientists never could have discovered, and the implications are absolutely mind-blowing. Stick around, because what you're about to hear may change how we think about space forever.
3I Atlas was discovered on July 1st by the NASA-funded Atlas survey. It was discovered using their telescope at Rio Hurtado in Chile, and it was first detected as a speck of light moving relative to background stars.
The AI revolution at NASA. When most people think of NASA, they picture rockets breaking Earth's atmosphere or astronauts floating inside the International Space Station. Yet some of the most groundbreaking work doesn't involve rockets at all. It happens inside computer labs. One of the most ambitious is the Quantum Artificial Intelligence Laboratory, known as QAIL, created through a partnership between NASA, Google, and the University's Space Research Association. QAIL was established to explore how quantum computing could transform space exploration. For years, it was more of a promise than a reality, its experiments fascinating but abstract. That all changed the moment 3I/ATLAS appeared. Discovered in July 2025, the comet immediately drew worldwide attention. Scientists knew from the start that it wasn't like anything formed in our solar system. Its trajectory, brightness, and composition marked it as something alien, an emissary from a distant star. Telescopes everywhere were pointed toward it, capturing every flicker and every emission of gas. The result was a flood of data, unlike anything astronomers had ever seen. Webb's spectrometers revealed chemical fingerprints. Hubble tracked brightness shifts that defied expectations. Ground observatories filled in details about dust, tail length, and movement. Faced with this torrent of numbers, researchers realized they had only one option: turn to the most advanced computing system available. The sheer amount of information gathered on 3 I/ATLAS was staggering. Webb alone produced terabytes of data from its infrared readings, each spectrum carrying clues about the gases released as the comet neared the Sun. Hubble added layers of precision, documenting subtle changes in brightness over time, which hinted at activity deep inside the comet's icy shell. Ground-based telescopes recorded dust structures, revealing turbulence that no one had anticipated. This was a tidal wave of information that could bury entire research teams for decades if they tried to analyze it manually. Even the most advanced classical supercomputers weren't enough. They could crunch numbers at incredible speed, but they couldn't connect the dots across thousands of overlapping variables without grinding to a halt. The comet's chemistry structure and orbital mechanics weren't isolated pieces. They were interlinked in complex ways. To understand one, you had to understand them all at once. That's where quantum AI came in. It offered something traditional computing could not: the ability to examine countless relationships simultaneously, revealing order hidden inside apparent chaos. But before the system could be unleashed, there was an enormous technical challenge: converting raw telescope data into a form that quantum algorithms could understand. The quantum breakthrough. Transforming the raw data into quantum states wasn't easy. teams of data engineers and physicists worked around the clock, rewriting numbers and measurements into quantum-friendly formats. Once completed, the data set was fed into NASA's quantum computers, and what followed astonished everyone. Within hours, the system began to reveal structures, trends, and relationships invisible to humans. Instead of noise, there were patterns. Instead of randomness, there was order. Where scientists saw a confusing cloud of information, the AII uncovered symmetry. The comet's chemical activity followed rhythms no one had recognized before. Its brightness fluctuations, once thought random, traced precise mathematical curves. Even its orbital mechanics, long considered straightforward, displayed anomalies that hinted at hidden forces. This was a deeper one, pulling secrets from the data that traditional methods would have missed entirely. Perhaps the most shocking revelation came from the comet's dust tail. To the naked eye, its structure looked chaotic, a messy trail of particles blown by solar winds. But when quantum AI stitched together data from multiple telescopes, faint spirals and shells emerged. These shapes, invisible in single snapshots, became clear only when millions of data points were layered into a single model. The comet's tail wasn't disorderly at all. It was patterned, as though it carried memory of the forces that shaped it long ago. The comet's movement offered another surprise. Astronomers assumed its orbit was simple, defined entirely by gravity. Yet the AI detected small but precise deviations. These weren't random jitters, but deliberate-seeming shifts, as if the comet was being nudged in a patterned way. Its chemistry, too, revealed repeating cycles, with compounds appearing and disappearing in synchronized sequences. For researchers, the realization was chilling. What they thought was random behavior was in fact governed by hidden rules they had never noticed before. The chemical fingerprint analysis. Traditional spectroscopy has long been a staple of astronomy. By splitting light into spectra, scientists can determine what chemicals are present. But with 3I/ATLAS, quantum AI went a step further. It elements mapped how they interacted. The comet contained unusual isotopes of carbon, oxygen, and sulfur, which pointed to an origin near a carbon-rich giant star billions of years ago. This meant the comet was a messenger carrying the chemical story of a distant star system. Even more remarkable was how the AI predicted certain rare molecules before astronomers looked for them. For example, it flagged faint signatures of exotic carbon compounds, and when researchers checked, those molecules were indeed present. What once seemed like a messy blend of ices and gases was revealed to be a carefully balanced system, with carbon dioxide playing a stabilizing role in the comet's long journey through interstellar space. The comet's chemistry wasn't random. It was a fingerprint of its ancient home. The AI didn't stop at chemistry. It reconstructed the comet's shape in 3 dimensions. Using telescope data from different angles, it created virtual blueprints that explained its odd brightness patterns. The model suggested that 3I/ATLAS might not be a single body at all, but a contact binary, 2 chunks of rock and ice loosely stuck together. This would explain why some regions were more active than others, and why certain jets of gas appeared only on one side. The AI even went further, identifying weak points where the comet could fracture. If it came too close to the Sun, it might split apart into smaller pieces, each carrying fragments of its ancient past. These predictions weren't guesses. They were based on detailed modeling of the comet's internal stresses, something no human analysis had managed before. Suddenly, scientists were predicting its future in real time. The orbital mechanics, mystery, and temperature, mapping breakthrough. At first glance, 3I/ATLAS seemed to be following a typical hyperbolic orbit, the kind you'd expect from an interstellar visitor passing quickly through the solar system. but the AI spotted tiny accelerations and slowdowns in its motion, buried deep within telescope data. These couldn't be explained by gravity alone. Instead, the answer lay in its outgassing, the jets of vapor that burst from its surface as sunlight warmed it. Most comets vent gas chaotically, producing unpredictable shifts in their paths. But 3I/ATLAS was different. Its outgassing was so precise that it gave the comet tiny rocket boosts in consistent directions. These boosts altered its trajectory in subtle but predictable ways. It was as though the comet was steering itself, not consciously of course, but through natural processes that followed patterns too complex for humans to spot. Only AI could uncover them, reshaping how astronomers thought about interstellar dynamics. NASA's infrared telescopes revealed another surprise. The comet didn't heat evenly. Some regions warmed quickly under sunlight, while others stayed frozen much longer. Quantum AI turned this data into detailed thermal maps, showing how heat traveled through the comet's surface and interior. The result was a portrait of incredible diversity, with pockets of volatile ices sitting next to regions of dense, insulating rock. Even stranger, the AI discovered feedback loops between heat and outgassing. As one region warmed and released gas, the escaping vapor cooled it back down, shifting activity to a different region. These cycles repeated with remarkable precision, creating waves of activity across the comet's surface. For the first time, astronomers could predict how it behaved hour by hour as it approached the Sun. The comparative analysis revolution. With quantum AI, NASA could compare 3I/ATLAS against thousands of known comets and asteroids in the solar system. The results were stunning. While it was clearly alien, the comet wasn't entirely unique. Some distant objects in the Oort cloud displayed faint similarities in chemistry and structure, hinting that interstellar and solar system comets might share ancient origins under unusual conditions. Even more intriguing, AI flagged several archived objects that might also have been interstellar visitors, misclassified in the past. These findings suggest that Earth may have already been visited by many more cosmic travelers than we realized. It's possible that the universe has been sending us messages for centuries. We just didn't have the technology to recognize them. AI also uncovered chemical mysteries hidden in plain sight. By examining every wavelength of light, it detected rare organic molecules and isotopic variants linked to ancient stellar processes. Some compounds were predicted by theory but had never been observed before. Their presence inside 3I/ATLAS confirmed ideas about how complex chemistry can emerge in deep space. But there were also spectral lines that didn't match any known molecule. These could be exotic compounds formed under extreme interstellar conditions, or familiar ones behaving in states rarely seen. Either way, they forced scientists to rethink what's possible in the chemistry of comets. For the first time, spectroscopy was predictive, showing how chemistry evolved as the comet approached the Sun. The Activity Prediction Model. Perhaps the most practical breakthrough was AI's ability to forecast the comet's future. By analyzing its past behavior, it built models that predicted brightness surges, chemical releases, and jet activity with remarkable accuracy. As 3I/ATLAS approached perihelion, these predictions came true almost exactly. The system even warned of possible fragmentation, identifying weak points that could cause the comet to split. While such an event wouldn't threaten Earth, it would complicate tracking and study. For astronomers, this predictive power was invaluable. Instead of reacting to surprises, they could plan observations in advance, ensuring no moment of the comet's journey was missed. Beyond raw predictions, AI revealed patterns that humans had overlooked entirely. By running unsupervised learning, it discovered cycles in the comet's activity that repeated with mathematical precision. What looked random in telescope data turned out to be governed by hidden laws. The AI also identified which observations were most valuable. By ranking telescope data according to predictive importance, it allowed scientists to focus limited resources where they mattered most. This efficiency meant more discoveries with fewer wasted hours, a major advantage when studying an object that would soon leave the solar system forever. The quantum advantage. The 3I/ATLAS project became one of the clearest demonstrations of quantum computing's advantage over classical systems. Where traditional machines would grind through possibilities one at a time, quantum systems explored them all simultaneously. This wasn't just faster, it allowed connections to be drawn across chemistry, physics, and orbital dynamics in ways no previous system could achieve. For NASA, it proved that quantum advantage isn't a distant dream, it's here now. The same methods used on the comet could be applied to exoplanet atmospheres, climate modeling on Mars, or even the search for extraterrestrial life. The project didn't just reveal a comet's secrets, it opened a door to the future of space science. The implications of the analysis stretched far beyond a single comet. By combining AI with quantum computing, NASA showed how science itself is changing. Instead of painstakingly testing one hypothesis after another, researchers can now explore entire landscapes of possibilities at once. It's a new way of doing astronomy, one that will accelerate discoveries across every field. There are even mission-level consequences. If AI can predict the behavior of interstellar objects, then one day spacecraft could be sent to intercept them. Probes might ride alongside comets from other star systems, gathering samples or transmitting close-up images. The lessons learned from 3I/ATLAS are already shaping proposals for the next generation of missions. Yet for all the breakthroughs, 3I/ATLAS remains mysterious. Every answer revealed by AI seemed to spark new questions. Where exactly did it form? How many like it are still drifting between the stars? And why did its chemistry and activity seem so precise compared to ordinary comets? As the comet continues its journey out of the solar system, data is still being collected. Each observation sharpens the models, preparing us for the next interstellar visitor. What's clear is that the universe is far stranger, richer, and more organized than we once believed. And thanks to quantum AI, we now have the tools to begin unlocking those secrets. Outro. NASA's experiment with 3I/ATLAS marked more than just a leap in astronomy. It showed us how quantum AI can reveal patterns and truths far beyond human reach. By uncovering hidden structures, strange chemistry, and rhythms that seemed almost designed, it proved that the universe holds secrets we can only unlock with tools that think differently than we do. And if one interstellar visitor carried so much mystery, it raises a thrilling possibility. What other cosmic revelations are waiting in the stars we've yet to study? Do you think 3I/ATLAS is just a comet? Or could it be something far more? Share your thoughts in the comments, and don't forget to subscribe, because the next mystery from deep space might already be on its way.